Hello everyone, welcome again to session 2 of the printed circuit board design principles and practices. My name is Walid, and we started our first session by asking the question, what is the future for the PCB designer? So the need to design current and evolving PCB technology is growing very fast, with more and more electronics such as Internet of Things becoming every day of our lives. The future of electronic design is very bright, and I encourage you to look into hardware design kind of professional work. Now, the industry needs more PCB designer, and those that are currently involved are reporting that their compensation and job satisfaction is on the rise. So if you have the passion for creating things and making them work, then designing printed circuit board might be what you are looking for. You will have much better success as a PCB designer if you have a degree that include PCB design curriculum, and you will have it in your transcript. So welcome again to the class. So the session for the outline for today's session is as follows. So we'll have a recap for session number 1 and a couple questions and answer to review. Then we will talk about electronic components because they are essential for PCB design or circuit design. We'll go over them very quickly, very briefly, and then we will talk about the electronic components model and what electronic component and ECAD tools mean. So then we will have the packages. We'll go over different packages for electronic component like through-hole packages, surface mount packages, and the variation of these packages. And the last thing we want to do is to take a look at the course project we need to work through this class. So let's get started. So PCBs, what kind of PCBs? As we mentioned in session number 1, we can classify PCBs into different classes based on the number of layers or the PCB technology or the type of the PCB itself. So when it comes to the number of layers, we can classify them or categorize them as a single-sided PCB where you have only one layer of traces and the other layer will have the component, or you have double-sided PCB where the traces are on top and bottom layer and you can have the components on the top or bottom or both layers, top and bottom. Or you have multi-layer PCB where you have top layer and bottom layer, you have traces on both layers, and then you have inner layers where you have traces as well, but the component is still on the top and bottom layer. Now, this is the first classification. The second classification is based on the structure of the PCB itself. So you might have rigid PCB. It's in the hardening state, like the motherboard or the regular board you see in our daily life. The second type is the flexible PCBs, and these become common in today's applications since we need to have smaller devices or smaller products, and we need these products to be flexible, like if you have fitness tracker, for instance, or smart watches. So this will be very helpful, but you need to be aware that the maximum number of layers you can go with flex PCB maybe up to 20 layer, comparing to the rigid PCB you can go up to 64 layer. Now the other type is mix, or you can call it hybrid. It's rigid and flexible PCB, and sometimes they call it rigid, flexible, rigid, because you have always a flexible PCB connecting two rigid boards. Here is an example in here we can see. So you have rigid board, and then you have a flex PCB in between. So you have 8 rigid boards in here and 7 flex PCBs, and you are constructing cube of printed circuit boards. So the last type I want to mention is called embedded PCBs, and this is also new technology, still very expensive. And the concept behind this is to integrate components inside the PCB, in the core of the PCB, but these component has to be at the silicon wafer level, so there is no packaging for the component. When you look at electronic component, for instance, this component in here, this might be a 5mm by 5mm component, but the silicon wafer chip inside this component is just 1mm by 1mm 1 millimeter, and the thickness of this chip is maybe quarter millimeter or less, couple micrometers. So when they integrate component, or they call it embedded PCB, they integrate only the wafer or the silicon chip, not the packaging. They don't need the packaging because the board itself will act as a packaging. Now, the PCB anatomy, we can divide the PCB into 6 items. The first one is called substrate or laminate. Basically, the substrate or laminate separate the copper layers, and they have 2 types. The first one is called pre-preg. Pre-preg is pre-impregnated bonding sheet. It's basically B stage. They call it B stage, meaning it's semi-hardening state of the resin. And it has to go through thermal settings to be fully hardened. The second one is called the core. And always the core separate 2 pre-breaks with the cover sheets on the top and bottom of the pre-break, of course. So the core is C stage because it's pre-cured dielectric material such as FR4 and made in the core factory. So here we can see different type of the laminate or different based on the size of these. So if we wanna, for instance, construct a PCB with 8 layers, all that we need is to select the laminate we need, and then we have a cover foil and cover foil on the top and bottom of these laminates. It goes from stage B into stage C, which is the thermal settings for the resin, and then you will get what is called cover clad laminate. And then in order to have more layers, you need to separate the cover clad laminate with the core. Here is an example that will make it clear. So you have first layer, second layer, and you have 2 sheets of 2116. So if we go back to session 1, you can find the thickness of this one, and now you can calculate the separation between layer 1 and 2. Then to separate the first cover clad laminate with the second cover clad laminate, you need to use a core. In this case, if you have 8 layers, you will have to use 4 pre-breaks and 3 cores to separate these pre-breaks. Now the second element are the traces. Basically the trace width and thickness determined by the capacity or the current capacity of the trace and the characteristic impedance in case of RF design or high-speed digital design. And here we can see all these traces, and we will talk about why these traces looks like zigzag in here. Basically, these traces belong to a differential signal where you need to have links matching. You need to do links matching, and that's why you see it like that. And we will talk about it in details about links matching and differential signals as well. So in the practical limitation for the traces is the minimum trace width and the spacing between the traces. When you go to a factory and request to fabricate a board, you need to understand the capability of the fabrication. What is the minimum trace I can use before you lay out your board, and what is the minimum spacing I can have also. It's not only the trace, it's also the through holes, the vias, etc. Now, when it comes to the third element, which are the holes, can be classified into pads, mounting holes, and vias. The pads can be defined as contact areas for soldering components, test point, and solder traps, and can have any. If we take a look at this example here, these are pads, and the first one here we have pads for surface mount component, which is integrated IC. Here we have a surface mount resistor, and these are the pads for the resistors. And here we have through hole pads for transistor, and here we have slots, and this is power jack. And these, they usually call them single layer pads for surface mount component, and these are called through hole pads for through hole components. And sometimes they call these multi-layer pads as well, also for through hole components. And the footprint for this, for instance, is a collection of pads. For IC1 is collection of 8 pads constructing one component. R1 is collection of 2 pads. Q1 is collection of 3 bats, and this power connector is collection of 3 slots or 3 bats. Mounting hole, on sometimes they call them mechanical holes, as we can see in here, and they are only used for mounting the boards or fixing the boards and stuff like that. They are not connected to any traces, and they don't have any electrical characteristic other than they are mechanical holes, and the cover is just to add a rigidity to the board at this point. Instead of have it, sometimes you can remove the cover and have it on only the fiber. The third type of holes are the vias. Vias, we have 5 different types of vias. The first one is the through-hole via that span from the top layer all the way to the bottom layer. The second type is the blind via that start on the surface layer and end on an inner layer. It's not necessary to end on 2, it can end on 3 or 4. The third type is buried via, as we can see in here. So it starts on an inner layer and end also on an inner layer. It doesn't go to the surface at all. So the fourth type is micro via, which connect to adjacent layers. It doesn't span for more than 2 layers. If it's a span another layer, it will be called skip via. So you will have start on the first layer, skip one layer, doesn't have any connection with this one, and then connect with the third one. Okay, let's take a look at how we can construct these vias and see them in real in Altium Designer environment. So if we go to Altium Designer, let's create a dummy BCB just for practicing. We will go back to this and like discuss it in details how we can construct the layer stack. So let's go to design. We have layer stack manager. Give it a moment. Now we have preset layer stack design we can use in here, so we don't have to design one. Let's say take the 8 layer stack, this guy. Now if we can take a look at the via type, the default via type, we only can see through-hole via that span from layer 1 through 2, 3, 4, 5, 6, 7 all the way to layer 8. Now let's take a look at, let's see, I need a 3D, show full stack, real layer height, and let's space them a little bit so we can see what's going on. So now here we can see the via. See the via in here? And this via go through layer 1, and here we have what we talked about earlier. So we have the cover layer, then we have 2 sheets of, let's say, what sheets did they use? So we have pre-break 2.8 mil and 2.8 mil, 2 sheets of dielectric or laminate material. Then we have a signal, another layer in here. Then we have a core, as we can see in here, it's 9 mil. Then we have, after the core, we have also 2 dielectric layers or laminate layers with 2 covers on the top, constructing the cover clade here. And then we have another core, 9 mil, same thing. After that, so we have cover, 2 laminate, then we have a cover, we have a core, and then the same thing. So 8 layer, we have 3 cores and 3 cover clade layers as well. And here you can see the name of each one of these. Now on the top, as we will see in the next slide, we have the solder mask layer. This is the solder mask layer, which is the green color on the top of the traces. And then we have the silk screen layer, which shows the component outlines, designators, or maybe even the values or any comment you want to put on the PCB. So here, let's go back. We have the through-hole via. We can see in here, this is the through-hole via. Let me zoom a little bit here. Okay. So let's add more vias into this to see. And let's add a via here. Let's say properties, and let's keep this duct here. And let's say this will go from inner layer 1 to inner layer 2. And you see, it's called buried via. We can add another buried via that goes from layer 3 all the way to layer 6. And this still is called buried via. Now let's add another via. And we need this to be micro via, as you can see in here. So here we have a micro via. And as we defined micro via, it's connect to adjacent layers. And then let's see skip via. If we add a skip via, so we have its type of micro via here. And if you connect 1 all the way to 2, we can see it's a skip, and it's called skip via now, and it's connect 1, skip 2 with 3. So if I say let's go to 4, it won't. It only skip 1 layer, so you are moving the whole via down by 1 layer. Okay, let's move this here a little bit. So what left? We need the blind via. The blind via start on a surface layer and end on an inner layer. So blind, top, and end on layer, maybe layer 4. This is called blind because it starts on the surface and on the inner. Let's put it into layer 4 and let's have a mirror of this. So the first blind via connect the top layer to the all the way to layer number 4, and the mirror one in the other way connect the bottom layer, which is surface layer from the bottom to and end on the inner layer as well. So we have through hole, buried, and buried via, micro via, skip via, and blind via. Let's add a mirror for these so we can see them in the visualization. Buried via, let's add a mirror for this one as well. And buried via, let's add a mirror for this one as well. So basically, if we want to talk briefly about this structure, we have through hole via connect 1 all the way to 8, and all the inner layers are included or connected to this via, so you can access this via from any layer. We have 2 buried vias in here, connect layer 2 and 3, and 6 and 7 only. So we have another layer, another buried via that span through the inner layers from 3 all the way to 7, and you can access this via from layer 4 and 5 as well. We have micro via connect this layer number 1 with layer number 2. We have another micro via connect number 8 with layer number 7. We have skip via with its mirror connect layer 2, skip layer 3, and connect layer 4. And the mirror one will connect layer 5, skip layer 6 to connect layer 7. So basically when I say it's skip, meaning you cannot access or connect with this via on the skip layer. Then we have a blind via that goes from the surface all the way to the inner layer, as we can see in here. So we'll connect layer 1, 2, 3, and 4. So you can access this via from layer 3 and 4 as well. So the mirror is the same thing. Now let's take a look at the visualizer right now. So put it here, we can see these guys. And let's unlock this. Here we go. Now we can see. So we have the through hole, this guy in here. We have the buried via in here. So only connect the traces on the second and third layer in here. So the other buried via in here connect layer 6 and 7. Then we have this buried via that span from layer 3 all the way to layer 7, this one, and it's accessible also from the layer between layer 3 and 7. We have this micro via in here. It's layer 1, you see how it connects with the trace and goes to layer 2, also connect with the trace, and it's only accessible from these two. Then we have the mirror micro via from layer 7 to 8. we have the skip via in here, and this is the important point I want to show. You see how the via is skipped in here, so it's not connected with the layer in between the two. You see, that's why they call it skip via. So this is basically how you can visualize these in Altium Designer, and it's basically we are building the stack right now. This is the layer stack, and we'll see that in details later when we talk about the design and start using Altium in much higher level. Now for the materials in Altium, even in Altium, let's say you can go to Tools, Material Library. Let's take a look. So also in session 1 we discussed the finish layer surface finish process. So after you put the solder mask, you have the surface finish process to protect the cover from oxidization. So, and we mentioned all these different type of surface finish, and we said the most common are the first two. HASL, you can go with leaded or lead-free in here, and you can select this material and you can change the color for it, and you can play with it, and or you can add a new material. If you have information about it, you can add it. So PCB layer material, these are the material you can see. So we have a foil for the cover, we have solder mask, we have flex layers, we have core material, different sizes, and these are all standard material, so you can use them right away. So we have a pre-preg, and also you can add any new materials you want in here. So, and we are gonna also discuss these in details later on. I'm just going over all these features in Altium Designer we are gonna use later on. And this is the preset layer. Also, you can create a type. We will discuss it later. I don't want to spend time on it right now because this is something required time. Also, we'll talk about rigid flex, how we can design rigid flex PCB where you have, let's say, two rigid PCB and you have a flex PCB connecting the two in the center. Also, printed electronics, we'll talk about it. So let's close Altium Designer and go back to the slides in here. So this is brief example of these different type of vias. So the fourth element we talk is the solder mask, which it's thin polymer layer deposited on the top and the bottom layer of the PCB, and this protects the outer layer or the cover on the top from oxidation and prevent solder bridges when you do soldering, because you see the solder mask in here separate this pad and this pad. So if you are doing soldering on this pad, you will this will help you now to over solder this pad as well. So, and this will be very helpful when it comes to wave or reflow soldering, as you saw in the video in the PCB assembly stages. And also the default color for these, which is most widely used, if you open any electronic device, you will see the PCBs, they are in green. So the green is basically the most common color, green coating, but also you can pick other colors as well. They are available in different shapes. I used to use red, for instance, for power electronics boards, and sometimes I used to use black solder mask when I have like transparent fiberglass on the top of the product and I don't want the green to be exposed. So black will help me to hide a little bit the PCB inside. You can pick the color you want. So the surface finish, it's basically referred or also referred as a solder coat or exposed conductor plating. So if surface finish is a common term, but if you hear solder coat or exposed conductor plating, it's the same thing. So this is the surface finish we mentioned, and we discussed in our first session 5 different type of surface finish, and we talked about the advantages and disadvantages of these different types. And we said the most common two are the tin solder or the EING, which is this one and this one. These are the most common two. So basically the surface finish, as you can see here, you have the PCB and you have here the copper pad, and the surface finish will come on the top of the surface pad only, because the other traces that are not pads are covered with the solder mask, which is the green area. Now the silk screen, which is the last element in the PCB anatomy, which is this white layer, shows the outlines of the components, and this will help during the assembly process as well, and it's basically applied on the top of the solder mask, and can be on the top layer only, or can be on the bottom layer only, or can be on both layers, on the top, on bottom. Only if you have a component on both layers you will need solder silk screen on both layers. But if you have only component on the top layer, then you need the outline and the designators for these components on the layer. That's why you use silk screen on that layer. Now, nothing prevents you from having silk screen on the bottom layer if you need to add some text. For instance, information about the company, or information about the board, whatever information you can add on it, or maybe a logo. You can add a logo on the silk screen layer. Now, let's go to the questions. So the first question I ask is to find out the maximum number of layers can be stacked up based on today's PCB design and manufacturing technology. And I received different answers from the students, and the maximum they were able to find is 50 layers. In fact, up to 64 layer PCB can be produced for commercial mass production type applications. More than 64 layers is not common for mass production applications, but you can go up to 100 layer when it comes to military type application, but these are not mass produced. They are in very small quantities. Now, you can take a look at, for instance, there are several companies that do up to 64 layers. This is one of the examples. You go to the capabilities, and inside the capabilities you can see they can do flex up to 20 layer, which is amazing, and they can do rigid up to 64 layers, and they can do rigid flex up to 20 layer as well, and these are the minimum size that they can do. So the smallest trace size and the spacing is 3 mil, and this is huge. And 3 mil, if they can do that, they have a very advanced PCB fabrication line and state-of-the-art machines, and they can do blind, buried, and stacked via. And for the BGAs, they can do 0.3 millimeter pitch spacing between two BGA bins. This is great. And the maximum board size they can do, or panel size, is 16 inch by 22 inch. This is the maximum PCB size. So this is one of the examples. There are so many other companies they can do 64 layers. If you can find more than 64 layers in the capability of the company, let me know. I never seen more than 64 layers. This is for the assembly and capability. Now, next, and we talked about what is the most critical stage in PCB fabrication and assembly. I received so many different answers from the students, and none of them is wrong. All of them are correct actually, because all of them are important stages. Missing up one stage will miss the whole process. However, in my opinion, spending enough amount of time on the design review, which is the first stage in PCB fabrication, would prevent a fabrication error and save time and money later, because you really don't want to fabricate something has a problem in the beginning. You need to discover this problem. So the process they do, which is the design review at the beginning, is very essential and very important. So when you send your Gerber files to a PCB fabrication company. They will review these Gerber files and they will come back to you. Either they will say the review process passed or not passed. If not passed, they will send you a report telling you, okay, here are the problem in the PCB and you need to fix your Gerber files before we can fabricate them. For instance, they will look if you have a minimum spacing between traces that is smaller what they can fabricate. They will look into the smaller widths of the traces you have on board. If they can fabricate all the way down to 5 mil trace widths, and if you have 4 mil or 3 mil trace, they will send it back to you. They said this cannot be fabricated. You need to change your trace width. And same case for also vias, and maybe if you have a buried via, they cannot make a buried via, they will send it back to you and they will tell you we cannot make a buried via. And what we can do, we can do through-hole via or micro via or whatever we can do. Now, when it comes to PCB assembly, today leaded solder is not allowed by law in many countries, particularly in European Union, and even if you are living in a country where leaded solder medium are allowed, you should consider using lead-free solder paste because leaded solder is poisoning, and that's why you should be very concerned about using leaded soldering. And if you have to use it, as I mentioned in the first session, in the prototype stage where I produce 1 or 2 boards for sampling, I use leaded solder with very little exposure to the soldering process. So I use a mask and I put it in a special room with vacuums and filters and stuff like that, because it's easier to replace a component in the prototyping stage and if I need to fix something. But this is 1 or 2 boards and it's not meant for customers, it's just in the lab. So I have full control over that. But once we go to mass production, and this goes to the customer, we use lead-free solder type of solder. Now, the main problem in using lead-free solder paste is the higher temperature needed for reflowing. Now, when using lead-free paste, you need to use a profile with high peak temperature, which is around 250 degrees C. And you will have to take special care to make sure that the overshoots are kept to the minimum. I'm talking about the overshoots in the soldering profile we see in here. So this is the soldering profile and this is the overshoot, and this has to be kept to the minimum, and this is basically copper second. I will explain it in a bit. So if this expand more than specific time, you might end up damaging all the component on the board and maybe the board itself. So when it comes to the most critical stage in PCB assembly, it's basically selecting the right soldering profile or reflow profile. When you go to the reflow oven machine, you have settings and you can select the profile or program profile and tune it according to the board you are soldering. So there is no specific profile for specific or generic profile for all boards. No, there are several factors that govern the profile you are using for soldering. So the factors are the maximum or the peak temperature the electronic components can handle, and also the type of the solder material you are using. So if you look at the soldering profile in here, it can be divided into 4 areas or 4 stages. The first stage is called preheat. Basically, in this stage, the flux solvent are evaporated during this phase, and your board is quickly brought into a little bit more than the half reflow temperature. And the second stage, where you have the temperature ramp up, and at this point the solvent evaporation complete and the flux starts its deoxidization action. So the ramp up is part of the reflow stage, So it's in blue in here. And here you have the actual melting of the alloy or the soldering material you are using, which forms the mechanical and electrical joints between the board bats and the component joints. The timing in this stage is very, very critical. A higher temperature could render uh, the board damaged, and lower temperature could also render bad joints, soldering joints. Then you have the last stage, which is the cool down or ramp down stage, which is quick cooling that desirable to create fiber grain structure and stronger joints as well. So if we take a look at the table in here we have lead-free reflow profile. This is the default for lead-free assembly, and these are defined by this standard, IBC standard. And this one for leaded solder, and this is the process, and also defined in this standard. And these are actually the maximum temperature you can use on the profile, or you can use the same profile. If we take a look at the preheat stage, usually it goes maybe to the middle temperature of the max temperature you can use in here. So it's around 150 minimum. So this is what for lead free you need 150 degrees C minimum to preheat the lead-free solder. If you take a look at leaded solder, you only need 100 degrees C. You have 50 degrees C difference between this one and this one. So you should not go more beyond the 200 degrees C for the maximum preheat temperature. On the lead-free, on the leaded, it's 150 degrees C. Now the preheat time, it's really take time. So it's between 1 minute to 3 minutes for the lead-free. For leaded, it's enough to have 1 minute to 2 minutes. That's it. Now then you have the critical point, which is the maximum temperature at here, which is only 3 seconds. Should not go more than 3 seconds at this point. And the temperature during this stage above TL is above 217 degrees C. Now this can go up to 250 degrees C when you talk about lead free, and can be around 109 200 for leaded solder in here. Then you have the cool down in here. You can go down, and this you have to ramp down by 6 degrees C per second in here. Same thing for the leaded solder. So all that you need to do when programming your reflow profiles is to go to the suggested profiles published by the producer of your solder paste and by the manufacturer of the component you have on board. That concludes the recap for the last session, and we can move forward. Now we have the electronic components, and this is a quick review because we are going to use electronic components in our design, and I thought it would be beneficial for all of you to have a quick review on the components. So basically we can divide the component or classify the component into 3 different groups. The first one are passive components, which are the components incapable of controlling current or providing power gain by means of another electrical signal. And these are called passive components, such as resistors, R, or inductors, capacitors, C. Transformers also are considered as passive component. And what about diodes? Diodes are semiconductor. Are they passive component or active components? In fact, diodes may be active or passive depending upon its property. A normal PN junction diode is passive, whereas a tunnel diode or Zener diode, for instance, are considered active component due to their negative resistance property. So passive component, they are solely depends upon active devices used for energy storage in case of the capacitors, discharge, oscillation, passive filtering, phase shifting applications, and so on. Now, active components, on the other hand, such as transistor, integrated circuit, the diodes also, they mentioned like the Zener diode or tunnel diode or any other type of diode, etc. They are considered as an active component. They produce energy to another circuit in the form of voltage or current, and they can control current direction and have a function of gain for the electronic circuits. That's why they are called active. So gains such as OPM, operational amplifiers, they can provide gain to the signal or to the circuit in different forms. Logic gates also are considered as an active component. So the last one is electromechanical. Some people classify electromechanical components as passive component, and that is correct. There is no problem with that. So electromechanical component, they have like electrical and mechanical properties such as relays and switches, etc. Now let's take there is graphics that is nice by Cordry. I have it here. So this is just example. You have passive component, you have the symbol, electrical symbol, and you have the physical footprint of the component. We have resistors. These are linear resistors, follow Ohm law. We have LDR, which is non-linear resistor, but still passive component. We have thermistor. These can be a negative temperature coefficient or positive temperature coefficient resistor, and also they are non-linear. So we have capacitors, non-linear, passive. We have inductors, switches, electromechanical, also classified as passive. We have variable resistor, they still passive. We have transformer, they are also passive. The active components such as transistors, some diodes, LEDs are considered, it's diode, but it's active. Photodiodes also, they are diode and they are active. Integrated circuit, all of them are active. Operational amplifiers, all of them are active. 7-segment displays, because they are composed of 7 LEDs per segment. Batteries or power sources are active because they control the power. Now, what is the construction of electronic components when it comes to ECAD tools or electronics computer aided design tools? So the component, let's say about Altium Designer itself, is composed of 5 elements. The components model is composed of 5 elements. The first one is schematic symbol. It's basically this symbol in here, and from its name we can know that this will be used in the schematic design. We have a BCB footprint, which is this yellow and red pads. The yellow is basically the outline of the components, and the red ones are the pads. These are SMD type pads. And also from its name we know that it will be used in the layout. Then we have 3D model, which is this guy in here that represent the actual physical component, and it's very useful for the modeling, and we will talk about all of these in details in the next slides. So we have the SPICE model. This is the SPICE model because Altium Designer itself has simulation, X signal simulation, SPICE simulation inside the tool. You can use it. Also, we have the signal integrity model, which is in here. And Altium also have signal integrity module based on the IBIS, which is input output buffer information specification. And let's take a look at each one of these. So basically, schematic symbols are a graphical representation of the electrical or electronic components in schematic diagram. Here we can see symbols. For instance, we have diode, capacitor, inductor, and these are the symbols are used in the schematic. So these are the pins on the schematic symbol. So the pins add electrical property to the component, and where you will connect the component with the other parts, you can use these pins. And these components or these symbols are legally standardized by so many different standards across the world. And there are different standards for these. The first one is the IEC, which is International Electromechanical Commission, also known as British standard 60617. If you search for this one, it's not free, you need to pay for it, but this is one of the standard in Europe. Also the ANSI standard, known also as IEEE standard 315. And this ANSI is American National Standard Institute. This is the acronyms for this, and this is widely used in the United States. Also, we have the IEEE, the Institute of Electrical and Electronics Engineering Standard, and also this standard defines only the graphical symbols for logic functions like this, how they should be drawn and how they should be used in schematic. And the last one is not really common, is the Australian standard AS1102, also define some regulation for the symbols. Now, the shape of the symbol might differ between standard to another. Some of the symbols, not all of them, especially when it comes to resistors, capacitors, and inductors. Here is some example. In the American standard, the resistor shape is defined as this, which is zigzag, and the inductor is defined in this shape. Now, when it comes to the IEC standard in Europe, the resistor is defined as a rectangle with the connection in here, or the pins, and the inductor is the solid rectangle in here. This is the difference in here. So when you design schematic, you will have the option to select which symbol you want to use. And also, if you see schematic while you are reviewing circuit or something, and you see this shape or this shape, they represent the same thing, which is the resistor. So don't get yourself confused with that. The standard not only define the shape of the symbol, but also define the naming scheme and numbering and the coding as well for these components, how they should be coded, how they should be noted. So if you take a look in here, so this is resistor, this is a capacitor, this is just an example. Let's start with the resistor. If you have resistor in ohm, in this case, you use the code R. And we'll see some example. Kilo ohm, it's K, mega ohm, giga ohm, tera ohm. When it comes to capacitors, you can use either capital P or small p. For picofarad, then we have capital N or small n for nanofarad. Microfarad, you can use mu or U or capital U. And millifarad, you can use small m or capital M. And for farad, which is the biggest code letter, is F, and it has to be capital F. Now, these are the name prefix for these. So pico, nano, micro, milli, and here kilo, mega, giga, tera. Now, the base or multiplier for these, basically the picofarad is 10 to the power minus 12 of the farad. And then we have 10 to the power minus 9 for the nano. The micro is 10 to the power minus 6. And when it comes to the resistor, it's the other way. If it's in ohm, it's 10 to the power 0, which is 1. If it's kilo ohm to the power 3, which is 1,000. And if it's mega ohm, it's 10 to the power 6, which is a million. Giga ohm 10 to the power 9, and then tera 10 to the power 12, which is the multiplier. Let's take some example in here. Now, before we take the example, I need to make very important note here. The common coding scheme in this standard avoids using a decimal separator and replaces the decimal separator with a letter closely associated with the prefix corresponding with the part's resistance or capacitance. For example, instead of using 0.47 ohm in here, as you can see, they use 0R as a separator 47. And from this, you know that this is 0.47 ohm resistor. For 0.7 ohm, it's 4R7. 47 ohm, you are moving the separator, and at the same time, R is the code letter. and 47 ohm in here. 470 ohm, you're still using the code letter R because the multiplier is 1. Now, it's kilo ohm, your multiplier is 1000 or 10 to the power 3. So 4.7 kilo ohm, it's marked as 4. You have the code letter K and 7. So this is 4.7K. 47 kilo ohm, it's 47K. Now, if you have 47.3 kilo ohm, it's basically you use 47K3. So basically you are using the code letter as a separator or this decimal separator. So 470 kilo ohm, 470K, if you have 4.7 mega ohm is 4M7 and so on. Same case for tera ohm and so on. Now, the second element is the footprint. So the footprints, as we can see here, if you open any data sheet, you will see the footprint with the dimension marking all of them. The footprints are patterns represents the actual physical side of a given component. And here we can see the width, the length, the spacing between the paths, the thickness of the component. These are SMD component, and this one is through components is BGA component. And they define where the component will be placed on the board, on the PCB, because you need to define space for this component and you need to define the paths for these leads as well and how they connect with the other components on board. And this the footprint can be created. This is not footprint, of course, this is the actual physical component, but you need to define a footprint where this component can sit and solder and connect with other components as well. So, and the footprints can be created from standard objects, just lines with soldering pads as well to provide the connectivity. And this footprint in the ECAD tools generally can embed the pads, the silk screen, the solder mask, the 3D model, and etc. All different kind of elements. And the pads of the given component can be either through hole, as we can see in here, or they can be surface mount, as we can see in here. Surface mount components. Now, let's take a look at through-hole parts. The through-hole parts, in this case, it's a kind of mounting scheme used for electronic components that involve the use of leaded component. As we can see, you will have a lead. For instance, this is a resistor, leaded resistor. You will have two leads in here, or if you have a diode, same thing. If you have a capacitor, same things. Or if you have integrated circuit, you have all these pins, for instance, in here. These all are leaded components, as you can see. Oh, we have some through SMT components, but these pins, all these are leaded components. You need to make a hole in the PCB to insert the component through the hole or the drill, and then you have a pad where you have the soldering joint to solder the component with the PCB. So in this case, the practice for this through-hole component is to insert the component from one side of the PCB and solder the component from the other side of the PCB, then you cut off these leads, extra leads. The soldering is done either by manual soldering, or they sometimes use something called soldering wave machine. Try to Google soldering wave machine, and it's very impressive how they do the soldering, where you have waves of solder and the board will go over these waves, and these leads will touch the solder wave and will pick up the solder at these soldering joints. It's very interesting. I have used one of these machines like 6 years ago, 7 years ago, even more than that actually. So the advantages of through-hole component, they are either for prototyping. It's very, because it's a big component, you can easily deal with it, remove it, put another one, and so on. And they have very strong physical structure and connection to the board as well, because they have to go through the hole all the way to the other layer, and you solder them from the other layer, and they count on this lead, which is strong enough to hold the whole board. And also they have much higher heat tolerance comparing to the surface mount components, and also they have much higher power handling capability because they are really physically big. Now, the problem with these, or the disadvantages with these, uh, you have to drill the port to fit these components. Drilling costs more when it comes to PCB fabrication. And also, they are bigger in size. That means they will take more space on the board. And if you are trying to minimize the size of your board for mobility, and in this case, through-hole components are a bad choice. Now, the assembly process is no longer fully automated. Some manual process has to get into, and in this case, the assembly will be much more expensive. And if you go online and try to request a code for PCB assembly, they will ask you how many through-hole components you have and how many surface mount components you have, and what is the size of each. And the through-hole component will add like significant cost to the assembly code. So because it requires some kind of manual process in this. And also slower speeds when it comes to signal integrity. It's not recommended to use through-hole components at all. And let's take a look before we switch to the surface mount components. Let's take a look at some through-hole components I have here. This is nice. You can download basically BCB Library from this link, and inside the directory you will see these files. These are very nice. These are 3D models, and you can see the footprint for these resistors. Now this is a capacitor, fuse, etc. These are leaded components. As you can see, polarized capacitors, you have a diode, p-n junction diode, and here we have ceramic capacitors. This is ceramic capacitor as well. All these are leaded components. You see, this is basically the hole you need to drill, and here is where the component can fit into. This is the actual size of the components. Same thing. We have polarized ceramic capacitors. We have electrolytic capacitors, polarized as well. We have LED, light emitting diode, and this is the footprint of each. You see? So the outline of the component, and then you have the holes. This is crystal for generating frequency, also oscillator. This is active crystal for generating frequency. These are TO220 kind of 3-pin chip. These can be transistors or voltage regulator. This is just examples, TO220. And this one is soldered to the board. It's right angle and soldered to the board. You have the pins goes in here, and then this heat sink goes on the board to dissipate the heat. And this one is vertical actually, TO220 also, but on this one you need to have a heat sink added to here and fixed to this hole. Here also, this is a kind of transistor with 8 pin. This is SIP. This is basically network resistor, you see. And this one has 1, 2, 3, 4, 5, 6, 7. It has 7 resistor inside, and the last pin is the common. And this is integrated circuit, also deep, dual inline package. You have 8 pin, and this comes up to 60 pin. So you have 8 pins. It goes in here. And this is socket for also through-hole dual inline package. This is bin header connectors, right angle bin header. This is BGA bin grid array. If any one of you saw the old CPUs, they had bins like that, and there is a socket underneath it, and the BGA chip will go into the socket. This is just example of through-hole components, and we will see another examples for SMD components. Now, surface mount components is a method of producing electronic circuits in which the components are mounted or placed directly onto the surface of the printed circuit board. In industry and in general, it has largely replaced the through-hole technology construction method of fitting components with wire leads into holes in the circuit board by the surface mount technology, because it's more efficient. Both technology, through-hole and surface mount technology, can be used on the same board, with the through-hole technology used for components not suitable for surface mounting, such as large transformer, for instance, and heatsink power semiconductors as well. When it comes to power electronics, most of these parts are through-hole because they have to handle a huge amount of power, and also they will dissipate a lot of heat. We cannot count on surface mount components for that, and we have to use through-hole components where we have a heatsink um, connected to these components. If we take a look here, we have a resistor in here. So this is a component body, and here we have the component contacts. So if you see this is capacitors in here. So this body in brown, and this is shiny metal on the side. These are the contact, and the component will be placed on the top or on the surface, because it can be on the top or the bottom of the PCB. It will be placed on the surface, and there will be a solder paste underneath it before they place it, and it will go through the reflow oven, and the reflow oven will melt down the solder paste, and it will connect the component contact with the pad on the PCB, as you can see in here. This is soldering. Now, the advantages of using surface mount component is small size. So in this case, you can make high dense board and make your product much smaller. Also, fast speed when it comes to signal integrity, transmission line, stuff like that. You cannot use a through hole, because every single hole on your PCB will create a delay for your signal, because the via represent, or the hole represent, a capacitors. And we'll talk about that in details later on. And also, when it comes to assembly, now you can use pick and place machine. The assembly process will be fully automated. The pick and place machine can place up to 100,000 components per hour. Imagine that speed. And you don't have to drill. That's mean in this case it's cheaper because you have less drilling. Not only that, if you don't have to drill, that's mean you have more space to fit components because you don't have holes at all. Now, the disadvantages, they have a weakly physical connection to the PCB because they are super tiny, and the joints between these components to the PCB is maybe quarter millimeter. So the physical connection is a little bit not strong, similar to the through-hole component. And also they have lower heat tolerance. That means we cannot count on them in high power applications. We have to go with lead components. And also there are some concerns when it comes to design for manufacturing. And also we'll talk about that in detail later on when we are ready to release a printed circuit board. Now let's take a look at some example. Here we have chip capacitors, chip resistors, chip inductors. And we'll talk about the footprint size in the next slide. And here you can see this is the footprint or land patterns. So this is the outline of the component, shows the outline. Here you have the bats, and here where the bats will fit. So you have extra size a little bit for the solder. And next, here we can see chip LED, light emitting diode, and here we have a diode, we have polarized capacitor, we have antenna, chip antenna, and you can see the footprint for these as well. So the sizes will be different as well, and we'll talk about them in a minute. Here you have capacitors, and we have diode, you have fuses, footprint, same case in here. We have molded LED, diode, capacitors, and diode. You see the footprint, and basically these connection point will be soldered to these pads in here, and the component will fit into this area specifically. So the edge of this in here will come all the way to this line in here. So you have enough space for soldering. And as you saw in the video, basically they will put the soldering paste first on these holes, or not holes, and these pads, sorry, and then they will place the component using pick and place machine. It will go through the reflow oven, and this will melt down and solder this joints to these pads. And You can view this file or download it from bcblibrary.com downloads and take a look at various types of surface mount components. And so these are diodes, fuses, resistor, but they are rounded in shape. This is small diodes, SOD. This another, these polarized capacitors, crystal oscillator. We saw a similar component in through-hole. So this is crystal, this is inductor, and so on. So this is a 3-pin component. These usually are transistors. This one, same thing, transistors. Here you can start seeing integrated circuit. And you see there is a package marking code SOT23-6. So anything after the dash represents the number of pins. So you have 6 pins. This is SOT23. This is the marking code for the package size in here. SOT23-8, same thing, same weights, but you have more pins. It's taller component, longer. So you can see here the landing pattern, and we'll talk about the difference between the footprint and landing pattern in the next slide. So basically, when you open these files, you are not seeing footprint, you are seeing land pattern. What is the difference between land pattern and footprint? These are a couple more examples. Please spend some time to review or take a look at these files. They are nice. These are big chips like microcontrollers, QFP, quad flat package. So you have up, I think 44 pin and goes up to 256 pin or even more. These are some examples. I'm not sure if they have, yeah, BGAs. I was looking for these. They have BGAs where the components are balls going underneath the component. Yep, these are some examples. Please spend some time to take a look at these. Now let's take a look. Now we still in the footprint. We will see land pattern versus footprint. What is really the difference between the two? So both manual and automated soldering processes require that the pads designed for a specific component to be larger than the leads of the pad, as we just mentioned, to which they will be soldered. So the land pattern should always be slightly larger than the footprint for any component. Other than that, it will be very hard to solder it and the joints will be very weak. So you must design your footprint or land pattern to have a little bit bigger pads than the component joints. Normally, you can find land pattern recommendation in the datasheet of the component. If you open datasheet of the component, go to the mechanical specification. At the end of the datasheet, you will see recommendation for the land pattern of any footprint are often used interchangeably in PCB assembly industry, but they are different. You need to be aware of that. So a given component could have multiple land patterns, but it's always have one footprint. And again, the footprint defines the physical size of the component, the actual physical size, the outline of the component, the spacing between the leads of the component or connection points. But the land pattern refers to the size of the pads and the outline of the component on the PCB board itself. And for both manual and automated soldering process, they require the pads designed for a specific part to be larger than the part itself on the PCB in order to have a very solid soldering joints on the board. And it's just slightly larger, and always you can find recommendation for the land pattern for a specific component in the datasheet of the component. If you go to the end of the datasheet, there are mechanical specification for the component where you can see a land pattern for that. And let's take a look at one example. For instance, this is a chip from Texas Instruments, LM5165. This is buck converter. If we go to the bottom here, let's see. So this is the 3D model of the chip, or the not 3D model, this is actual chip actually. You can see the connection points in here. These are the pads, and this is basically heatsink for the chip. And this is the footprint diagram. This is basically the actual dimension of the chip and the actual spacing between these connection points, and you see the spacing between two pins, it's 0.5 millimeter. That's it. So the spacing from the center of this pad to the center of this pad is 0.5 millimeter. This is fine pitch component. Now, here you can see the land pattern example, which is recommended by Texas Instruments for this component. Now, if you see the size of this bin on the chip and compare it to the size of this pad, this one is a little bit or slightly bigger than the pads to provide a good connectivity between the pads on the PCB and the pad on the chip itself. So the recommendation for the land pattern is always there in the data sheet. Here is an example, you see. This is the soldering pad recommended on the PCB. And these are also land pattern for the solder-based examples. Also, they provide a land pattern for the solder-based layer. And we'll talk about that. This is just an example, quick example. You can find it almost in all the data sheets. So you don't have to worry about it. How can I find it? Now the land pattern, we know that the footprint has one shape of the component, which is defined, which is the manufactured on the chip. We cannot change that. But land pattern could have different shapes, and we'll see examples in the next slide. Now, the naming convention for these land patterns or footprint when you design a library are defined in the IBC standard. The IBC is the Association Connecting Electronics Industries, and is a trade association whose aim is to standardize the assembly and production requirements of electronic equipment and assemblies. So when you design a library, you need to follow a specific standard if you need to have a standardized library that can be shared among different entities. And the IBC standards also define 3 density level for land pattern. The first one is called level A, which is the maximum or most. And this one is basically you have the biggest recommended land pattern for the pads of a component. And this only is used in low density product application. The second one is called level B, which is the median or nominal, or sometimes they call it N, normal, which is a moderate level of components density. And in this case, the pattern of the land pattern pads are designed according to the datasheet itself. So the level C is minimum least, which is used when you have a really high density board, and where the land pattern pads are really just enough to fit the component soldering joints over there. And here we have some examples. So first, land pattern can have different components pads. Here we see land pattern for the same component, and look at the pads. So we can have either rectangle, oblong, D shape. In here you have different shape, it's up to you. We know that these are slightly bigger than the actual bed of the component. Also, the IBC standard defines 3 density level. As we said, we have density level A. You see the beds are bigger than the bins of the components. Or density level B, they are in the normal or medium. And density level C, you see they are almost the same size of the component itself. This is for a chip. This is for resistor or capacitor or inductor, SMD 2-pin component, as you can see. So what is the difference between that? When I do have space on board, I prefer to go with density level A because I will have a stronger soldering joint with the component. But if your component is really dense and you have the component next to the other, you have so many components on board and you need to minimize the size of your board. In this case, you cannot afford to have a big pads on board for these components. In this case, you need to space the component further to fit on board. In this case, you can go with density level C. So you only have the right size of the soldering pad to fit your component. And we will talk about this when we start learning how to design a library, how to meet the IBC standards for during the design. You don't have to worry about that because Altium Designer will generate all three different variation of the density level automatically. So you just specify if you need A or B or C, or you need all of them, and Altium will generate that for you based on the IBC standard that is integrated inside Altium Designer. I just want to mention that because when in the next session we will start using Altium, when you go to select a component from the component panel, you will have the choice to select either density level A or B or C. This is just quick overview. We'll go deep later on. Now, the third element in the electronic component model is the 3D model. If you recall session 1, we said in the design world, the cost of fixing a mistake goes up to 10-fold each step of the way. So it costs 10 times as much to fix a mistake during prototyping comparing to fix it during design. Then 10 times more again to fix that same mistake during production, and 10 times more again to fix it once the product has been shipped. These are rough approximations, but a cost increase in the order of 1,000 times to fix a mistake when the product is in the customer's hand, compared to fixing it during design stage. That's a strong motivator to get the right or to get it right during the design process. Now, today's electronics products are compact and tight packed. It's really tight. Looks at the fitness tracker. There is a circuit board and a lot of electronics inside that, and it's highly compact. So comes in an unusual shape and may well have a PCB that is folded to fit into the case. Now, to design a product like this, you need to be able to model the PCB in 3D so you can visualize the finished board, perform 3D clearance checking, and transfer the loaded board to the mechanical computer-aided design domain. And you have like tight collaboration between the mechanical design and electrical design. And to do this, you need to have a 3D model for every single component in your board. Usually the ECAD engineer design the board in 2 dimensions and size it according to the positioning in the case critical element using dimensions provided by the mechanical engineer. Now, once the board is done, it will be sent to the mechanical engineer. The mechanical engineer will try to fit the actual physical board that is implemented in this case in here into the enclosure. Now, it might not fit, the clearances might not be right, and we might have a lot of problems. Now, to help avoid mistakes and that add multiplier factor to the cost, we need to have 3-dimensional ECAD and MCAD design environment where you can collaborate between the mechanical design and electrical design before you build your board. This will save a lot of cost. And Altium Designer allow to do that. And in this case, you need to have, as we said, we need to have a 3D model for every single component on the board. And this 3D model represents the actual physical size of the component, as we can see here. This is a board, and this is courtesy of Altium. And here we can see we have the USB connector, we have the earphone connector, and we have the LEDs, etc. Now, within Altium Designer, in here, we can import a 3D model for the enclosure, and we can do, in this case, clearances test to make sure that nothing from the board will interfere with the enclosure at any single point before we build the board. Now, if anything need to be moved or need to be adjusted, we can do that before the build. Once we have this collaboration between mechanical design and electrical design, we can release the board and fabricate it. This is how important the 3D model during this design. Okay. Now, SPICE model and signal integrity model in here. They simulate the behavior of the connected component using the SPICE simulator integrated inside Altium Designer. And the SPICE model or the signal integrity model are usually sourced from the component manufacturer. You can go to the component website and search for the SPICE libraries and you can find them. This isn't just example from ST. They have couple part numbers and I'm just presenting this as an example. You can go and find these model and integrate them into the Altium Designer if you are creating this components, and you can use them later because in Altium Designer itself you can do some SPICE analysis and signal integrity analysis as well, which is very helpful during the design stage. Now, if you cannot find the SPICE model or signal integrity model and you don't care about the analysis, signal integrity analysis or SPICE analysis within Altium, you don't have to worry about. It's not necessary to integrate these models when you create a component in Altium Designer, because sometimes you might want to do your SPICE simulation in third-party tools like LT-SPICE, for instance, and which is what I do usually. I don't count on Altium Designer to do SPICE analysis. Sometimes I use signal integrity analysis, and we can talk about that as well in our next sessions or coming sessions. Now this will conclude the electronic component models, which is schematic symbol, PCB footprint, 3D model, and we will have the chance to create libraries and create components in Altium Designer. We will start by creating schematic symbol. It's just basic shapes. We can create symbols, and also Altium Designer integrate symbol wizard, where you can run a wizard and just specify the symbol you want to create, and the wizard will create that for you. You don't have to worry about it. Footprint also same case. There is an IBC footprint wizard which will create the footprint for you. You don't have to create anything from scratch. Everything will be automated. It's very handy. You will talk about it. 3D model, you can import the 3D model from external open source resources such as, this is one of the very famous website. You can search for a 3D model. Now let's say I'm searching for O4, O2, cap. So you can see the 3D model in here, for instance. You can click on it and you need to sign in and download this, and you can import it to Altium Designer. We'll talk about this as well later on, but it's just quick look. Now, when it comes to the packages of the component, the package size of the component itself depends upon several parameters, such as how much power the component can handle in case of 2, 3, 4, and 5 terminal packages, resistors, capacitors, transistors, and so on, or the functionality provided by the component, such as the number of the input-output of the microcontroller. So if you have microcontroller with 28 pin, so maybe the IOs on that microcontroller are around 22 input-output pin. If you need more IOs, like I need 50 input-output pins, you might need to go into a microcontroller that has at least 64 pin, and so on. So there is no specific rule to specify the package size of the component and the number of the pin on the component, other than the functionality and also how much power the component can handle. Now, the two terminal packages are usually resistors, inductors, capacitors, and diodes as well. Here is some examples. We have the metric standard and the imperial standards as well. And we will see these in detail, so we'll take a look. For instance, if I need to search for surface mount resistor on DigiKey. DigiKey is a component provider, component vendor that provide components from different vendors, components resource website. So let's take a look at DigiKey, for instance, to explain this. Let's go to DigiKey and let's say ceramic cap 0.1 microfarad. So ceramic capacitors, let's expand this. More filters, thanks. And we need surface mount only. I don't want a 3-hole. And so here I need also 0.1 microfarad in terms of capacitors. You can filter that out. It's very handy and very easy to find a component in DGKey. I like it and I use it all the time, and I source all the component from DGKey as well. So here, if you can take a look in here, so you can see the package size or case 0201. These are IBC standard. They are defined in IBC standard. It's not like that every single company will go and make a component in size according to their own specification. No, everyone is following a specific standard in creating the component packages. It's not random, and it's standardized process. So you'll see 0201, 0202, and here this imperial, and this you have the metric size 0603, and so on. You can see all these different sizes, and these are standardized in the IBC standard as well. So if we go back to our slide, for 2-pin connector, usually RLCs, you will find these values: 0402 in the metric, 0603, and basically 0402 is 0.4 by 0.2 millimeter component. 0603 is 0.6 by 0.3 millimeter component. You see how tiny these components are. And the smallest component I use, or always I use 0402 if I don't need high power resistor or capacitors or big value capacitor. So the value of the capacitor is also the bigger capacitance, you need to go with a bigger component as well. And also the voltage of the component also control the size. So here is some example. Let's say I need a component that can take 100 volt. Now you can see here we can have 0201 as small as 0201. Let's filter it out. Now it's much higher. Okay. Now the smallest you can do is 0402. You cannot go smaller right now. If you have a much higher voltage or much higher capacitance, you need to have a bigger component as well. Now the variation of the electronic components package are countless. There is no way we can find all these different variables or variations. As we saw in the PDF file, I showed you just some examples. So if you go to, for instance, Wikipedia on this page, the surface mount technology, you will see if you have 2-terminal packages, these are the metric and these are the imperial, and you can see the different variation you have. So 06, 03, 08, 05, and so on. These are really small components. When it comes to capacitors, they use different marking for that. So these are also based on standard. When it comes to aluminum capacitors, this is what they use. When it comes to small outline diodes, SOD, you have these codes, and we will see all that when we start doing the design. And the difference is basically the size of the component, how small or how big, and how small and how big is controlled also by how much power this component can handle, and the number of the pins and the functionality as well. So there are several parameters that control the size and the package of the component as well. Please take a look at these different variations. They are countless. Now when it comes, these are only up to 5 or 6 terminal packages. These are just examples. When it comes to dual inline, you have these, and if in every single one of these you have so many different variations. It's endless. And you don't have to worry about that. Everything will be easy to use, and just import libraries in Altium Designer and use it. So try to download this tool from BCB Library and review the materials. Once you download this, you can go to this folder where you install the component or the tool, and there is a documents folder. Look at or look inside the document folder, you will see a lot of examples about the through-hole parts and the surface mount part as well. It's very handy. Now, so course project. This is the last slide in our today session. So in the next session, we'll get your hand dirty and start real hands-on work. So also in the coming weeks, we will have part of the weekly sessions to introduce the theory and discuss best practices, and the other part to apply theory into practice using Altium Designer. So just the first session were just an introduction to some basics. We still have to dig deep into the theory, and when it comes to signal integrity, transmission lines, electromagnetic interference, we will start study these concepts and talk about the best practices, how we can avoid electromagnetic interference, for instance, and how we can protect our board from electrostatic discharge, and how we can guarantee high level of signal integrity on the boards, and what is the theory behind all these concepts. This will be discussed in details, and then how we can apply all these into our design in real world. Also, we'll see that in Altium Designer. So for the course project, meaning during this course, we will try to use this sensor. I designed myself, so I own the sensor, and there is no a problem with using that. So I allow that for the student to use it during the design, but this sensor is part of application patent, so it's protected. Don't try to commercialize it or use it for commercial application because it's protected. And we will discuss the design concept for this sensor, because this sensor is kind of Internet of Things design concept, and you will learn not only how to design a PCB, but also how to design a real product, and the PCB is part of it. So we'll go through process and how we select these components, and what are the parameters and selection criteria for every single component, and how we can design such a board. And this is very small board. If you want to know the actual size of the board, this is the actual size of the board. This is the real board. On this slide, you have the 3D model. On this part, you have the actual board. This is the top side of the board. Here you have power connector, you have antenna, GPS module, you have wireless transceiver, you have micro SD card, and other components on board as well. So this is 1 cent. If you are not familiar with the cent, this is 19 millimeter diameter. This is just 19 millimeter diameter. So this sensor is basically 45 millimeter long, 30 millimeter in weights, and only 6 millimeter thickness. This is very small components. It's like it's on the finger. You can put it on your finger. So this is 4-layer PCB. We have top layer, bottom layer, and 2 inner layers that are used for the power as power planes, and we will use it as a reference for the examples during this course. So we'll discuss it in details, and the next session I will provide a video on getting started with Altium Designer, and it will be very, very interesting. Okay, thank you all for your time, and see you next.